Welcome back. Next we'll consider angular velocity and angular acceleration in some more detail. So let's consider the rotation of a rigid body about an axis defined by the unit normal vector n, which is normal to the plane of rotation of point P. Point P has position vector r, and r makes an angle phi to n. The position of P is theta, and the velocity vector tangent to the circle v is dr dt, or r dot. Now the magnitude of v is ds dt, where s is arc length around the arc, which would be r d theta dt. Now r here is the radius in the plane of rotation of the point P, which is therefore r sine phi. So therefore ds dt equals little r theta dot sine phi, where little r is the magnitude of the position vector r, and theta dot is the magnitude of the angular velocity vector omega. So the magnitude of the velocity equals the magnitude of the radius times the magnitude of the angular velocity times sine of phi, where the angular velocity vector has magnitude theta dot and direction n. Now, if we make the construction omega cross r and take its magnitude, then its magnitude would be the magnitude of omega times the magnitude of r times the sine of phi, which is ds dt, which is the magnitude of v, as we found above. Therefore, given that v is perpendicular to the plane of omega and r, we can therefore write that omega cross r equals ds dt times the unit vector v divided by the magnitude of v, but ds dt is the magnitude of v, so therefore omega cross r is v. And so we now have a vector definition of the angular velocity omega in terms of the position vector and the velocity vector. So v, which is r dot, is omega cross r, where the magnitude of omega is theta dot. The acceleration a is dv dt, which from our previous slide is d dt of omega cross r. Applying the product rule is d omega dt cross r plus omega cross dr dt, which is d omega dt cross r plus omega cross v. And d omega dt is alpha, the angular acceleration vector, so we get that a is equal to alpha cross r plus omega cross v. So the angular acceleration alpha also acts along the axis of n, and its magnitude is omega dot or theta double dot. Now, making use of, again, v equals omega cross r, that gives us that a equals alpha cross r, and substituting omega cross r here, we get omega cross r. And so looking at the direction of this vector, we can see that these are the tangential component of a, and that this term here is the radial component of the acceleration. So let's consider the tangent and normal components of the acceleration of a point in the plane normal to the axis of rotation that is rotating in a circular motion about the origin. So our point is P with position vector r, and it has angular velocity omega, which is theta dot times n, where n is a unit normal vector perpendicular to the plane. The velocity v equals omega cross r, and omega is theta dot, so v equals theta dot n cross r, and the magnitude of v equals r theta dot, where r is the magnitude of the position vector r. Now let's consider the tangent and normal components of the acceleration. Again, omega equals theta dot n, and alpha, the angular acceleration, equals theta double dot n. And the acceleration vector, a, has a tangent component parallel to the circumferential unit vector e theta, and a normal component parallel to the radial unit vector er. So from the previous slide, recall that the acceleration a is alpha cross r plus omega cross r, which is a vector triple product. Now, recall from vector analysis the vector triple product a cross b cross c equals b times a dot c minus c times a dot b. In this case, a and b are omega, so we get that omega cross r equals omega times omega dot r minus r times omega dot omega. Well, omega and r are orthogonal to each other, so this dot product is 0. Omega dot omega is the square of the magnitude of the angular velocity, which is theta dot squared. So therefore a equals theta double dot n cross r times e sub r minus theta dot squared times r times e sub r. Therefore, the tangent component of the acceleration is r theta double dot. That's because the tangent direction is the direction of n cross e sub r, which is perpendicular to the plane of the normal in r. So that's the tangent direction. So therefore, r theta double dot is the tangent component of the acceleration. And the normal component, a sub n, is minus r theta dot squared, which is minus r omega squared. So the tangent component of the acceleration is r times the magnitude of the angular acceleration. The normal component is minus r times the square of the angular velocity magnitude. Let's look at some special cases of rotation about a fixed axis. Again, omega is theta dot n, so the magnitude of omega is theta dot. The magnitude of the angular acceleration is d dt of the magnitude of omega, which is d omega dt, or applying the chain rule, d omega d theta dt, which is omega d theta. So when you need to integrate an angular acceleration as a function of theta, you can use this form. A special case would be a uniform rotation in which the acceleration is 0. For example, theta equals theta naught plus omega t. A uniformly accelerated rotation with a constant acceleration could be omega equals omega naught plus the magnitude of the acceleration times t, which would mean that theta equals theta naught plus omega naught t plus 1/2 alpha t squared, integrating. And then taking the square of omega, we get omega equals omega naught squared plus 2 omega naught alpha t plus alpha squared t squared, where alpha is the magnitude of the acceleration vector. And so that means that omega squared is omega naught squared plus 2 alpha times omega naught t plus 1/2 alpha t, which is omega naught squared plus 2 alpha times theta minus theta naught. Now let's consider the angular velocity and acceleration when the motion of the particle p also includes a radial component, so that there's both a theta and an r component to the trajectory of p. So v equals r dot equals omega cross r, and a, the acceleration vector, equals r double dot or v dot, which is equal to alpha cross r plus omega cross r, as we saw before, where alpha is omega dot is theta double dot n, where n is the unit normal vector to the plane of v and r. Now in this problem, the radial unit vector would have Cartesian components of cosine theta, sine theta, and 0. So cosine theta, sine theta, and 0. And the theta unit vector will be perpendicular, so it will have components minus sine theta, cosine theta, 0. And just to check that these are in fact orthogonal, if we take ER dot E theta, we can see that we get 0. So we can use these expressions to compute the derivatives of the radial and theta unit vectors with respect to theta. So dER d theta will be minus sine theta plus cosine theta, 0, which is the same as E theta. Therefore, we can write dER equals E theta d theta. Similarly, taking the derivative of E theta with respect to theta, we get minus cosine theta minus sine theta, 0, which is equal to minus ER, which says that dE theta equals minus ER d theta. So now, if the particle velocity, v, is equal to r dot ER, so that's the radial component, plus r theta dot, which is the circumferential component, times E theta, then the particle acceleration, a, is equal to v dot, which is the first derivative of this expression, so r double dot ER plus r dot times ER dot plus r dot times theta dot times E theta plus r times theta double dot times E theta plus r times theta dot times E theta dot. And from the results we obtained above, since dER equals E theta d theta, then ER dot must equal theta dot times E theta. In other words, dER dt equals d theta dt E theta. And E theta dot, which is dE theta dt, equals minus theta dot ER, which allows us then to write A equals R double dot minus R theta dot squared times ER, which is the radial component, plus R theta double dot plus 2R dot theta dot times E theta, which is the circumferential component of the acceleration. In this case, when the motion includes a change of radius as well as a change of angle. Let's consider the general rotation of a rigid body about an axis through the origin O. At a point P with position vector r, the angular velocity is omega and the angular acceleration is alpha. The velocity of point P is v, which equals dr dt, or r dot, and is equal to omega cross r. And the acceleration of P, a, is equal to alpha cross r plus omega cross r, where alpha equals omega dot. Now this is the most general rotation, and in this case the angular acceleration alpha can be thought of as the velocity of the tip of the angular velocity vector. So far we've considered rigid body rotations. Now let's consider a general rigid body motion, which would consist of a translation and a rotation. So point A with position vector r sub A has angular velocity omega, angular acceleration alpha, and point B, which has position relative to A of RB relative to A, which would be RB minus RA. So the velocity at point B, V sub B, equals V sub A plus the velocity of B relative to A, which equals V sub A plus omega cross R of B relative to A. So the rotation about a. Similarly, for the acceleration, we can write that a sub b equals a sub a plus a of b relative to a. This is a sub a plus alpha cross r of b relative to a plus omega cross r of b relative to a. So in other words, the most general motion of a rigid body is equivalent to a translation defined by the motion of a reference particle, in this case A, and a rotation about the fixed point A. Let's consider a two-dimensional example of a general plane motion consisting of a translation and a rotation in a plane. So A1 goes to A2 and B1 goes to B2 as this body translates and rotates. So the translation we can show as the vector connecting A1 to A2, and there's a parallel vector connecting B1 to B1 prime. Then to get from B1 prime to B2, this must be a rotation. So considering this a little bit further, if A has velocity VA and B has velocity VB, that can be decomposed into the sum of the translation where A and B both translate with a velocity of VA, plus a rotation of B about A with an angular velocity omega. So this is the velocity of B relative to A, which is equivalent to angular velocity omega, referenced to a new reference frame x prime y prime that has A as its origin. So we've said that a plane motion can be represented as the sum of the translation of an arbitrary reference point, in this case A, and a rotation about that reference point. And we can write for the accelerations similarly that a sub b equals a sub a plus a of b relative to a. And the tangent component of the relative acceleration is r alpha. And the normal component of the relative acceleration is r omega squared, where r here is measured from the new origin at A.